worth like messaging your channel. But yeah, if you guys are interested in learning more on the technical side of this, definitely read your article. It was like written super well. So yeah. So in terms of overview,
yeah, so this is going to be Unit 6 in the Megadoc, both the technical and literacy article, and link there as always. We're going to do Pai's lecture on reinforcement learning. Everyone give him a round of applause. He made some amazing slides. We're very excited. Again, as always, one synthesis question due Tuesday, and then all the questions and your project, again, technical and literacy, due this Thursday. So make sure you finish that. And also, the end of the thing, or the end of the quarter is coming up, so make sure you're keeping on track with all of your assignments. You don't want to have like 3 or 4 projects due on like finals week or something. So make sure you're keeping on track. You have Thanksgiving break too. Catch up on some work if you need to. So definitely, yeah, make sure you're not like overloading yourself in the last few weeks of the quarter.
And today's we'll start reaching out if there's any like major blank spots missing and stuff, so they can definitely help you as well. And also, yeah, make sure you guys are paying attention to this lecture because there's something at the end. Hint, hint, wink, wink. But yeah. So yeah, everybody get your notes up, get ready. And can we get a round of applause?
All right, so yeah, as they mentioned, this week is reinforcement learning. Just to go over last week's problems, you guys had like, what was your favorite karaoke song? A lot of you guys said you don't do karaoke. That's kind of weird. I don't know. I like singing. And then you guys had other songs and other things that you mentioned. For this week's attendance, yeah, go ahead and just scan this, and there should be a question. Yeah, just scan the appropriate one. And let me know, yeah, I'll wait for you guys. You had the last step? You I think it's been a year or two.
I feel it's difficult to like question mark.
Yeah, just look up at the screen when you guys are done. All right, I think we're good to go. So yeah, this week's reinforcement learning for you. Feel free to ask any questions anytime. I'm serious here. This stuff is pretty complex, and a little at the end, the math gets pretty hard. And just ask any questions. I'll try to answer. So here's a real quick roadmap. You'll start off just learning what's RL, then we'll go to some vocab. Go along a few examples along the way, and then we'll go to the math. And the first little bit of the math is probabilistic equations. If you guys have taken 312 or anything like that, you might know that, or any math class, that might be a little familiar, but Q learning math is a little different, and that might be new to you guys. So what is RL? Yeah, so RL involves formalizing and studying how autonomous agents interact within a real or simulated environment. And deep reinforcement learning is the form of deep RL, which applies deep learning techniques to these agents, enhancing and complexing their size, or like their strength. So just to demonstrate, I have a quick video here. I don't know if you guys may have already watched it, but here we go. Yeah, so I remember watching this video a few years ago, and that really got me interested in reinforcement learning in general. It was just like this dude who like plays a game and he uses an AI to beat a pretty hard to track, and he trains the AI. He says it took over 3 years. I don't know if it's simulation data or actual data. I don't doubt it took 3 actual years. I don't doubt that it actually took 3 years because it's really long, as you guys will learn. It takes really long to train the data and just like parse and not do all that. So it could take anywhere from like 3 to even more years to just simulate it. And just a few examples that we have real quick of reinforcement learning is, so there's this OpenAI model called Dexterity Dactyl. It's like a robotic hand of some sort. And it's like trained entirely on simulations and transfers its knowledge to reality. So it like simulates all the data and everything, and then it like transfers it to the hand. And it learns to scratch. So we use the general purpose RL algorithm, OpenAI 5. If you guys have heard of it, it's also famous for like a Dota. It played Dota from scratch, and it beat like some professionals, which I found was really cool. So it beat like a team of professional Dota players, just simulation off like the data. And I found that really cool how like a robot can beat players who train for over 10 years. And I found that really cool. And another thing is it showed that it's possible to train agents in like a simulation without fully accurate models. So you don't need like a fully accurate model to train the data. It can just be any agent in a somewhat good simulation. And just training off the data, it's always going to be pretty well. Moving on, just a little more looking at the data, more parsing dexterity and dactyl. We have, as I mentioned before, the majority of the time is spent just training the model. So in dactyl, simple tasks such as rotating an object takes 3 years without randomization and over 100 years with randomization. Just to put that into reference, you guys probably learned to snap your fingers when you were like 2 or 3 years old, right? Well, you started off like with the concept of snapping your fingers. It probably took like a day or two just to grasp and then like be able to do it. It probably took you guys a day or two, right? But for the model, it will like start off from scratch. It'll start off the same strength, like the same level as you, but it'll take many years to train. And you can see right there, if you have like all randomization, it will take much longer. So you can see that it takes like 100 years to do 100 years worth of simulations versus the other one is it takes a little slower. It takes 100 years for the randomization one to do like 40 goals, and it takes a little less for the non-randomization one. Randomization is pretty useful in like the data as it accounts for all real world things that might happen. In real world, it's not always going to be perfect. Like the data isn't always going to be perfect. Any data just going to be. It's better if it's like randomized accounting for all possible like situations. And so there are their own benefits to randomization and no randomization. So if you guys have any questions, just let me know. I can talk a little more about that. All right, here's for a little bit more terminology. If you guys have any questions, do you guys have any questions so far? Yeah, go ahead.
So when you were talking about randomization, what exactly did it do to the data?
Yeah, so going back, it's just like, so there's inputs, there's like certain inputs and outputs that within the model, which we'll learn a little later, they'll just tweak around those numbers and randomize them a little bit, try to get the most optimal solution and the most optimal output, and then they'll tweak that output, turn it back into the input for like the algorithm again. It'll just repeat that whole process. It's better if it's like randomized. It's not better, but it's like accounting for randomization is better in real scenarios, as the world's not perfect, as I mentioned. So just randomizing the inputs is often a pretty good idea. Any other questions? Go ahead.
Why does it take so long?
Yeah, so it takes pretty long to. Yes, it takes really long. I don't quite know the answer to that, but there's just a lot of things that it has to answer. Like, if you guys saw the video, you can see all the different possibilities and every single thing it has to calculate. All those, like, there's probably hundreds of thousands of simulations within there. Each taking their own time to like finish out and end at a state that's terminated. So simulating like each of those ideas and then adjusting for it just takes really long. And there's a lot of data and numbers to calculate. So that's why it takes so long. Anyone else? Oh yeah, so moving on, we have the terminology. All right, the first and one of the most important things that you guys should probably know is the state and action pair. The states are often denoted with a subscript with respect to time, and they have Markovian property, where only current states matter and not previous and / past history states. I'll touch up on that a little more. And the state transitions are often dictated by environmental dynamics. So the environment and the surroundings also have a pretty big impact on the states. And for the action themselves, they're often denoted with subscript with respect to time as well. And they're taken by the agent after giving the agent the current state. So you input the state and they'll give out an action. These often impact the next state. So whatever the agent does in that state, it will have an impact on the next one. And the main idea is that state action pairs result in a reward. So if you guys look at the example with the Flappy Bird, I think we've all played the game before, but just the point is to get like as far to the right as possible. And the state of this game could be basically like that's just snapshot. If you have if you have a complex enough like algorithm, computer vision, that has like computer vision involved, you wouldn't need to give the numbers specifically, and you could just input an image and it will tell you like the action or reaction or action or to either go up or down. It will just output that, but you will, in normal scenarios where you won't have access to the computer vision model, you could just give it the numbers and it'll tell you what action or reaction or action to take. And yeah, the action, as I mentioned, the only thing you can really control in Flappy Bird is to either go up or to go down. And so that action, given the state, it'll give either an action to go up or down. And just, yeah, as I mentioned, the main idea is that the action and the state give a reward. In Flappy Bird, the reward is, like the thing we're trying to maximize is how far to the right or how many pipes it crosses. And the reward is just basically like one to the score. So you're trying to maximize the score, basically. You're just trying to basically maximize the score. So the reward would just add to the score. Any questions? All right, yeah, go ahead and reflect. Think about how humans often learn through trial and error, right? What's the time that you had to learn anything this way? Just describe this experience and explain some similarities and differences between your learning process and how reinforcement learning operates. And just talk amongst yourselves and just talk about that for a minute.
I was thinking about like solving the Rubik's Cube and how like the AI would do different from how I do it. So like when I learned to trial and error as well. And when I learned to trial and error, I was doing it. But I feel like for me it was just like it was the feeling of how the cube was moving but that's not what like, my AI would do. It was like recognize the image and I would I would pick steps that would take away from the thing to solve it faster or later. Whereas I guess an AI wouldn't do that because it has like positive negative reinforcement, so keep searching for the next positive step.
What do you think? Let's be on the recording. So fun. I was thinking, I mean, I told 3 people this already, but like walking is a pretty good one, like as a child.
Yeah, I was thinking of just like riding a bike.
Oh, that's a good one.
Yeah.
That's so like cute. Like, I like that one. That's a good one.
All right, yeah. Anyone have any examples? I've heard some pretty good ones.
Never mind. I've been silent.
Any examples? Yeah, go ahead.
Solving the Rubik's Cube.
Yeah, I agree that solving the Rubik's Cube, if you like don't know any strategies at all, it's gonna be pretty hard, right?
Yeah.
Like you can't just like move the things around and find the best possible, just find a way to solve it. It doesn't really work like that. So I do agree that it's a pretty good way to like coordinate the two like, trial and error and reinforcement learning. Anyone else?
If there's no hands, he's gonna call him.
I feel like I heard a good one over there. I feel like you had a good one. Would you wanna describe it?
Stand up.
Yeah, go ahead.
I said when you play basketball and you're shooting, to like keep correcting your shot.
Yeah, yeah, that sounds pretty good. Like in order to become the best basketball player, you gotta like learn how to adjust and take your prior history into account. So an example I had was just like learning to ride a bike. Basically, like you start off, you're pretty wobbly without the tricycles. You're pretty wobbly. If you lean too much to the left, you're gonna like end up on the floor, onto the left, right? If you lean up too much to the right, you're gonna end up too much on the right. So you need to learn how to like balance the two of them, and just the only real way to do that is through trial and error, right? So that's what I had, and like you could probably implement the reward system into there as well. if you like lean too much to the left, you're your elbow's gonna get scratched or your knees are gonna get bent or whatever. And if you lean too much to the right, the same thing is gonna happen. But like if you lean right in that angle, something magical will happen, I guess. Your parents might be proud in my scenario, that was mine. Or else you might have like riding a bike sounds pretty cool, and just like the breeze on your back, that might be a good reward for you guys. So I think that was my example. I found that pretty intuitive and it helped me learn the concepts a little easier. All right, here's some more key concepts that are pretty useful and in reinforcement learning. So the first is an agent, right? The computer model, the agent's basically a computer model that interacts with the environment and learns from it through the form of a reward. It follows a policy pi, which we'll touch up on a little later. And an example of this is just like a robot in a maze or an AI game player. And speaking of, the environment is going to be the environment that an agent acts in. I don't know why I mentioned environment within environment, but it's just like the thing that an agent acts in. It can change based on the actions that an agent takes, and it also may change on its own. An example of this is just chess or robotics or like a robotics competition or just puzzles in general. And lastly, the reward. A reward is basically a signal that indicates how good the agent did. For example, it could be +1 points for doing something good and -1 points for doing something bad. Or it could also be something like time efficiency related. So if it's better for a model to last longer, then you could give more points like the more seconds or the more minutes that it lasts. And looking at the top right image, we have like basically it's just a graph. So let's say you start off with the agent, right? The agent gives you an action. You feed that action into the environment, and that environment outputs a next state and a reward. You input the reward and the next state back into the agent, and it should output another action. And then you input that, input that action back into the environment, and it just creates a whole loop and optimizes each of the outputs, and that's basically how the model learns. All right, for this example, I don't know if you guys are familiar with the snake game. I know I used to play that pretty often back in middle school and high school. But yeah, we can talk about the agent environment and reward system for Snake. So the agent is going to be like the snake or the model that plays the game. So it's going to be like either moving. It's going to be like the thing that controls the mind of the game, basically. And the environment is going to be the board. In this case, it looks like it's 16 by 16 or maybe 20 by 20. It's going to be like a board. It could be represented by arrays or anything. And looks like the environment is probably also going to have the apple itself in, because that's a part of the environment. It could also be part of the state, and that's just something you'll have to figure out yourself. And the reward system is basically, the reward system for the game is just going to be like basically the length of the snake or the number of apples eaten. You're trying to optimize that, so the longer the snake in like a specific state of the game, you know that's you're doing something good, basically. And so, yeah, that's basically an example I found pretty intuitive. Do you guys have any questions about this? All right, here's some more key concepts. So the trajectory tau is a sequence of states and actions that end in a terminal state. For example, in the state game, it could be going up, to the right, down, to the left, just any of these, and then like ending at its place. Just anything where it like just moves along. It just moves along basically a path or a trajectory. And the return, or the R of tau, is going to be the total reward over a trajectory. So it's basically asking, what are we trying to maximize, or what's the goal? In our snake example, it's basically the length of the snake or the number of apples that it ate. And the discounting factor, or gamma, it's a little harder to understand, but it's basically using like an infinite horizon discounted returns, and it basically weighs the more stuff currently than future stuff. So for example, in snake, let's say you have an apple that's like a couple states away, only 3 or 4 states away. You'd rather go to that apple than go to an apple that's like 20 states away, somewhere way off in the corner. As that's going to be harder to get, it's going to be harder to navigate. It's just going to take more computing power and more states. It's just going to have to go through more states. And we have this example of trajectory again. So it starts off here, it goes through here. It just basically skips through all these, and it just ends at this final position. The final position doesn't always have to be like the most optimal path or whatever. It can always just be, the trajectory in general doesn't have to be the most optimal way. It can just be any specific path that goes along like that. And for the concept of the gamma, or the discounting factor, the R of tau just represents the reward. It's going to be equal to the sum of gamma gamma to the sum of time with gamma to the time power times the reward at a specific state with time t. If that sounds a little complex, it's not that bad. It's basically saying, let's say you have 3 different reward values. One reward value with let's say you have one reward that gives you 1 point, another reward that gives you 2 points, and then another one that gives you 5. Let's say you parse them in 1, 2, 5. So you go to the first one first, then you go to the second, then you go to the 2-pointer first, second, and then you go to the 5-pointer. That's basically saying it's less optimal than going to the 5 one first. No, yeah, it's less optimal than going to the 5, then the 2, then the 1. You just want to value bigger rewards first. Anyone have any questions? Yep.
Just wondering, how is the discounting factor different from the reward when it's a -1, for example? Or like
Yeah, so the discounting factor isn't really isn't like I don't know how to explain it. So it's scaling the thing. So let's say if the reward is negative, it's going to scale that at, let's say the discounting factor, for example, is 0.5. That's a pretty steep factor. Let's say the first state is going to be 1 times the reward that you get. So let's say the reward is -5. Your total is going to be basically -5. And then let's say the next state, your reward is -10. So that one you do really bad. It's going to be -10 times 0.5. So now it's going to be slightly less. It's going to be slightly less negative. I guess in negative it works a little weird if you have a negative reward and a positive discounting factor, but it's going to basically scale your rewards. That's basically what it's doing. Any other questions? All right, yeah, before we move to a little more mathy part, let's look at another example real quick. Let's say one of our players in the system is just a student and the other is a reinforcement learning bot. What would the agent environment and rewards be? And give an example of a trajectory. It doesn't have to terminate, just could be anything. And what are we trying to maximize? And just one more question, give an example of why we should have a discounting factor in our bot. Yeah, just talk amongst yourselves, and I'll call out a few people if no one raises their hands.
Trajectories and number of moves, trying to maximize checkmate and even more moves you take, the reward you check.
the agents be all
Yeah, I think you could argue it, yeah. Yeah, because I feel like with this, it's like, it depends on like what you pick as your agent. You can like change your environment based on that too. So,
the agent be more like the player, like
yeah. And that way, like, you could also track like the movements, if it like goes back or not. The technical article also does a really good job of like explaining like the agent and like all the movements. I don't know, are you on the technical track? Okay, yeah.
does I've never why, I kind of understand like eating, like
Eating other things, yeah.
have you ever heard of what also like the images in that thing?
So there's like short-term and long-term reward. So like eating would be like a short-term reward, but then sometimes like in reinforcement learning, there's also something that's like long-term. So it looks at like after you do a bunch of moves, like did you end up winning, and then based on that it'll like track it. So it'll also like every time you take like one piece of your movement somewhere, it'll like track like the likelihood of you winning based on like future things, and then that could be like your reward. It's like the tiny portion of your likelihood of winning. But then if you like take another move that like increases your likelihood, then all of a sudden it takes away from your overall reward. But that is like a really tricky question because like what do you base it on, you know? How much of a reward do you get for a good move versus bad move for some reason?
Yeah, that was next. So the overall increasing
Yeah, so that's like another really good question because like if you give all the rewards at the beginning, then maybe like the agent like does cover a good moves.
Will gamma always be less than
Reward, I guess.
Is there a case where you want gamma
I think position, so it
one
really
reward
depends
to
on
increase
which
the increase the number
but
of
usually I think they'll have like
hyper-specific
so
scenarios
like each step you get a little bit of reward or a little bit
But the thing is, I've only ever learned about
That
it
way you
here.
can like learn throughout
I haven't
versus like
heard of a rule.
kind
Yeah,
of
that's
like
probably actually.
not learning anything.
Work with RL more
Oh, I
than
should've done
I used to focus more on criticism.
So they try to do it for like every single step.
Yeah, so like your piece getting in that like a negative.
Yeah.
Okay. So are there like different possibilities then? Since there's like, I guess maybe neutral or like negative, just like that's really or oh wait, that's and then there's also the additional like end and then there's the short term criticism. So would there be like how
It really like depends on how you promote it. I think like in the article I remember it was from the short term report, and it was kind of like talking about that, like prioritizing that over like long term stuff. But
He said
it
he
like
could
it really
apply
just
in
changes based
different
on
parts of situations. Like for example, in the first
like
moves of a
you can
chess
do
game,
both. It just like
you
depends
want
on the situation.
further rewards,
I
like
don't know
rewards
too
that
much
are
about chess,
worse to
but,
have
like,
like greater
like,
impact
like short-term
because you're looking in the
long
long term, right?
because you're working towards your end goal.
That's kind of like
And,
Anyone have any
it's
answers?
like one, but it's like always.
But the negative gamma makes sense. For the road to keep flipping with every move.
You wanna go ahead? I heard you talking about it. You wanna go ahead?
Honestly, look at that because
A lot of that stuff is like theoretically discussed, but like real world.
Yeah, so you're on the right track, but the agent is going to be more the guy or not the guy, the bot controlling the pieces in general. Each piece isn't really going to have its own agent, as you can only move one piece at a time. You can only have you can have more than one agent, but it's better if you have one and just further enhance that one agent. So that one agent can control all the pieces, and the environment, yeah, you mentioned is correct. The whole board in general is the environment, and the slate. And the rewards is going to be, you could have your own function for the rewards. Like I know if you have a good enough bot, the rewards is going to be like an evaluator, just adding to the evaluation. And so if you take a piece, you would basically add to the evaluation, you have a bigger lead. And if you lose a piece, you subtract from the evaluation, you have less pieces, you have less of a chance to win. And so an example of a trajectory, does anyone have any? All right, so a trajectory, it could basically be any move that could be played. So let's say you go your queen, you move it from here to here. I know that's not the best move. That's just an example I had. Let's say you move your queen to here. That immediately gets rid of your queen. That's not going to be the most optimal. It's just going to give you a really bad reward for that move. But then this piece could take it back. That's another part of the trajectory. And let's say you take that piece back again. That could be another trajectory. It doesn't have to be always a capturing move. It can just be any move in general. And what are we trying to maximize? Yeah, that really cuts back to the rewards, I guess. It's going to be, we're just trying to maximize the score or maximize the chance of winning. And we can have either a function or anything that sets it up that calculates that. And yeah, and then our example why you should have a discount factor in our bot. Does anyone have any answer to this? Go ahead.
It's because maybe because like the chessboard has like so many moves, and although I guess you could calculate 10, 20 moves at advance. At some point, it's just it's gonna take an exponential amount of computing power. So you should just value the current largest advantage.
Yeah, that's a pretty good thought process. Yeah, I know even 5 moves deep, there's almost trillions of different possibilities for just 5 moves deep in chess. And if you're in a middle game position like this, there's probably millions, billions of outcomes that you can have just within 5 moves, right? So it's going to be really hard to calculate all the possible outcomes and all the possible things. But also, yeah, so let's say an example here would be, let's say 20 moves down the line, you can see a path where you checkmate the king, right? But also, let's say you're in mate in 1, you're gonna get mated in the next move. Would you rather want to take that mate in 1 than winning the game would you want to save that mate in 1 rather than winning the game in 20 moves down the line, as you won't really get that chance, and a lot could change within that. All right, here's the more math heavy part of this. It's going to be a lot of probabilistic equations and DQ theory. Anyone have any questions so far? All right, get ready for some notes. So yeah, the RL problem is whatever the choice of return measure, whether you have the gamma or no gamma, and whatever the choice of policy, the goal in RL is to select a policy which maximizes the expected return when the agent acts according to it. For example, let's say we have a policy pi, and that represents the policy that the agent follows. Let's say our policy only ever turns right. Then just intuitively, that probability that it turns left is going to be 0. And we have a probability of tau given a pi. That's what this line means. Probability of tau given a pi means that given we have a policy pi, what's its chance that the policy results in a trajectory tau? All right, we have this like long equation right here. We'll dig briefly into that in a minute. Go ahead and here's an example. So let's say we have 2 starting nodes. The probability of starting here is going to be 0.75, let's say. That leaves the probability of starting at the orange node, 0.25. You'll have these calculated, like the probability of starting in each specific place. You'll have that calculated when you actually like code or develop the function. That'll just be something you have stored. And yeah, so let's say the probability that it goes to the left is going to be 0.25%. That's basically going to be the p of the next state given the state in action that happened before, and then multiplied by the policy that the action and the state. So basically it means just like the probability that a certain move happens given the policy and the previous state. So right here we have, if we're in here and we go left, that probability is going to be 0.25% or 0.25. And then from this state right here, let's say we have a policy that goes right. Then and right at almost like 99% probability. We have the total probability that the total probability of tau given the policy p is just going to be 0.75 times 0.25 times 0.99. We can just cancel out the 0.99 as it's basically 1. So it's just going to be 1/4 of 75, which is roughly 0.21, 0.21 point something, or 0.21 something something. So that's going to be the probability that it takes this trajectory and ends up at this node right here. Any questions? Yeah, and then the trajectory is just going to be like the path that it takes. So from here to go to there, there's a lot of different trajectories you can take. You can either go here, here, and let's say there's another one that goes here, here. You can take several different trajectories, but the specific one we're asking about is here, here, here. All right, expected return. So J of pi represents the expected return of a policy pi. We want to basically maximize J of pi. Think about it like this. A good policy should try and trade trajectories with higher returns. So in turn, this value increases if the trajectory with high returns is selected more. For example, we can look at the equation right here. Probability of tau given pi times the reward of tau, and we're just trying to basically maximize that. For example, if you look at this equation here, it looks a little complex at first, but the more you look at it, it kind of gets easier. It's basically saying the expected value of a policy pi is going to be equal to all the trajectories. You don't really have to calculate all the trajectories, as I say here. It's like a theoretical thing. You can just calculate your specific trajectories within your policy. As if you have like millions of trajectories, for example, if you have in a chess game, there's at least like 100 moves you can play probably, given a specific position. You're gonna have to calculate probably like billions of different calculations. It's gonna be a little harder. So it's going to be the probability of that trajectory given pi times the reward of that trajectory over all possible trajectories. That's going to give you the expected return of the trajectory. And then the central optimization problem in RL can be expressed as this. So it's just P star, or the most optimal policy. Whenever you see star, it's just going to basically mean most optimal or like optimal. It's just going to equal the max of the previous trajectory. So it's going to be max of the expected value of the policy. So yeah, it's a little complex at first, but I'll show a few more things that might make it easier. Any questions? Go ahead.
Is the pi in this equation different from pi from the previous slide?
No, it's going to be the same. It just represents a policy. It can be either written up or something else, like I mentioned. So like taking a right, for example, policy with like where you can only take a right. In this scenario, let's say you have all the possible trajectories. It can go anywhere. you can just automatically like cancel out any trajectory that goes left and leave that as, with like a probability of 0. And so it's just like, it doesn't have to be, it can be coded up or like described, but that's gonna be policy, it's just gonna be the same thing. Not to be confused with 3.1 or, yeah, like the math one, it's a little different. Any other questions? All right. Just a quick break from the math. Can you think of a real world example where, outside of like the generic games or robotics, that could benefit from reinforcement learning? Yeah, in cases where the agents might make decisions that like directly impact human life, like, such as like healthcare or finance, what ethical considerations must be also considered? And like specifically by like the people who develop the programs or use the programs. Just talk amongst yourselves, and I'll give a quick example if no one has any. No one has any.
Considerations like this. We don't have the same goals that AI does, so it means that that tries to maximize the and to be detriment to us. Like if we're going to make more paper, that's done all the things to be as accurate as possible. That's not what we want. That's like program doesn't do. All right. Does anyone have any examples that they talked about? Go ahead.
For the second one, ethical consideration could be with somebody who implemented the rewards, either maliciously or ignorantly, put in rewards that be hurtful to people.
Yeah, for sure. That's definitely something that you gotta consider. Like whoever developed it, they could have malicious intents or something not like that doesn't support all of like humankind. Any other examples? Go ahead.
You said like ChatGPT to like refine some of the responses.
Yeah, I know like ChatGPT has that disclaimer that like it's not always correct or whatever. That could be the same for this. It's not always gonna like give it most optimal, best solution possible, as there's a lot that it has to parse and the data is gonna be pretty wrong. In terms of what I was talking about, like ethical considerations, I was gonna think about like. Oh, go ahead first.
Oh no, I thought like real world examples like navigation, like the shortest route to get to a place, you could use.
Yeah, like the shortest route, it can like accept like specific path, like highways or whatever, and you can like make sure. It's pretty hard to like if you don't want to take highways for some reason. It's pretty hard to. You have to like set that. You have to develop that with yourself, like the best possible path. The best possible path without going through highways, you're gonna have to develop that yourself. And in terms of what I was thinking about with ethicals, I was thinking like the stock market basically. So let's say you have a stock bot or like an algorithmic bot that optimizes like the best trades. And let's say there's a company that does like, let's say it has 1,000% returns within the year. That sounds pretty crazy. The bot will probably almost always select that company, right? But what if that company is engaging in like child labor or something? That's something that humans will consider about, but not the bot. It's gonna always go for the most optimal. It's gonna always go for the most optimal solution. So it won't really consider about the ethics behind it. All right, here's more of the math again. This is the optimal action value function, or Q star of S of A, which gives the expected return if you start in the state S and take an action A, and then forever act according to the most optimal policy in the environment. So this is basically where the core of Q learning comes from, and our goal is to try to estimate this Q star function. It doesn't, like whenever you start, it doesn't exist. You have to basically make that up on your own, and you have to basically train it. It's like training just a normal, it's just training a normal like AI or anything. You have to train it and get the most optimal Q star. And yeah, you'll just fully flesh that out, and it won't really be fleshed out fully until you complete the model. And we'll dig a little deeper into the equation in the next slides. But anyone have any questions about Q star? All right. So yeah, it's called the Bellman equation, and an intuitive look on why the Bellman self-satisfiability condition is useful for training RL models. Remember, we're trying to estimate Q star, which is the Q function that can be used to maximize our expected return. So let's say we have this trajectory here. All right, let's say we have this trajectory here, and if what we're trying to estimate satisfies this condition, then we're using the Q function here. So let's say we solve for the Q function at this node right here, which is going to be S and then A. If using it there should evaluate to be the same as using the function on the next state plus the reward of using it at the previous state in the action. Because we always want to estimate the reward system of S and A. If that doesn't make the most sense, you can kind of look at the equation itself. The more you look at the equation, I guess it kind of makes sense. Like the more you look at it, it's a little easier to understand. It's basically does look like it's recursion in a way that it's calling another copy of itself. But more importantly, it's like calling the future state of itself. In recursion, it's more like it calls the previous state n minus 1 or whatever. This one basically calls n plus 1. So it's looking into the future and basically accounting for the rewards and finding the most optimal rewards of your given node. All right, yeah. So how exactly is the model trained? So the symbol on the left is the loss or the difference between received and expected Q values. So it's called the temporal difference loss, and it's basically Q of S and A. So it's Q and S and H of here minus the minus and then parentheses R plus the gamma factor, which is the decay factor of max of Q, and then the next state. So it looks into like I said, it looks into the next state and basically approximates. This one actually doesn't approximate. My bad. This one doesn't approximate. It like just finds the most optimal. It finds the answer or the rewards for the next state, and then it calculates that and gives the reward for this state. And it finds the difference between basically your predicted and your actual value. And then it uses this number, the temporal loss, to basically account for changing the parameters up a little bit in the future renditions of running the algorithm. And as it says right there, it has connections to neuroscience, as it's pretty similar to how dopamine receptors work. If you think about it, let's say you plan to go skydiving for the first time like next week. Leading up to that event, you should be pretty scared, right? You'll probably be really scared, but I mean, it's your first time. It's gonna be something. It's gonna be like giving you the thrills. And then either during or after skydiving, you're gonna feel pretty you're gonna basically feel pretty high. It's gonna be like an event that was pretty surreal. And then like right after, I know a lot of people, they don't really go skydiving once, they go more than once, many times. So it's kind of like how your dopamine receptors start pulling down, and it's basically like training. Training is to account for that situation. Anyone have any questions about either this or the neuroscience? All right, here we go. We have that basically was the last section of the slides. We have a little Kahoot to do at the end, so if you guys could just pull out your phone. If you guys could just pull out your phone, and if you want to do the Kahoot, I'll load it up. And I'll give you guys the code in seconds. Oh yeah, here's the code. Just feel free to scan it in. Once we get enough people, start. tried to make it not so math heavy, so if you guys don't feel confident, it should be a pretty easy, just recap of the previous questions. Alright, I think we have 31 people. Is anyone having trouble logging in? Or is anyone having trouble? Okay, yeah, just go ahead. If you want, yeah, go ahead and change your icon to a brain, I guess.
No.
You don't have to, but it's up to you. Alright, I think we have enough people. Is anyone else going to join or anything? Alright.
So bad.
And then we can assign it.
I'll use it to these.
Do you guys all like smile and look at the screen? Like I think you're having so much fun.
Alright, yeah, so the Markovian property basically just means that only the current state matters and not like prior history. All the other ones were pretty easy, so it looks like the majority of people got it. And it basically means, for like this question, you might have been getting the states mixed up with the rewards or the actions. The actions are the ones where like the state matters, and then the state gives an action to take. So it's a little confusing, but it just basically means the prior states have no effect. All right, here's the next question. Yeah, looks like almost everyone got this one correct. It's saying, yeah, how much of the future rewards are valued compared to immediate ones? So it's just, yeah, as I mentioned, it's the gamma or the discount factor. It's basically valuing closer ones more than farther ones. It can, I don't know any instance of where it could be like more than one. So like where it could value farther ones a little more than the closer ones. But I might do a little research, and if you guys are interested, let me know. I'll try to find if I can find anything where farther ones are more valued. Yeah, so it looks like the majority of you guys got this one as well. It's just asking what does Q of S and A represent, which is the expected return of taking an action action A in a state S. Yeah, it's just basically the only option that really made sense. The other ones, the number of times state S was visited, as I mentioned, it doesn't store, like, it doesn't matter the previous states, so that one wouldn't really make sense. And the other ones, they make sense, but I think this was the only one that made most sense. This is an update on leaderboards. Yeah, so a trajectory is just a sequence of states and actions. That's basically what it is. It ends in like it could end in like an end node or an end trajectory. And yeah, looks like the majority of you guys got this one as well. Yeah, here's another one. Yeah, so whenever an agent takes an action in reinforcement learning, it basically just receives a reward and moves on to the next stage, given the new inputs and the new rewards. So yeah, looks like the majority of you guys got this one as well. Here's another one. Yeah, so the action A is just going to represent I guess, okay, it could represent, this was a little confusing. I meant to say like the current X and Y coordinates of the bird, but it's just going to represent whether to go up or down. So that's whatever the action is going to represent.
Well, if you're doing left, right, then you know which one you're selecting. Okay.
Yeah, this one was a little more complex, but it basically just means the one that's like closest. It can mean like if the rewards are set correctly, it could be like the case where the left one has a little more, even though the bigger value is located at the very right. It could be if the leftmost values are more heavy weighted than the rightmost values in certain scenarios. It could be like the opposite, but if you do the math, it's fairly close between these. So it's gonna be this one that's weighed the most, or that has the biggest reward sequence. Alright, yeah, so randomization is important because it helps just handle for real world like scenarios that might happen. The real world isn't always like perfect, and it's not, the data that you'll get isn't always perfect, so it's just better if you randomize it and account for everything. Yeah, so I'm surprised not many of you clicked 3.1415. But yeah, pi just represents the agent's policy. It could be like either only going right or only going left or anything like that. The ones of you who said the total rewards, that's just going to be R of tau. That's going to be basically what the total rewards outputs. That's a little different than the policy. Alright, for the last question, why might Markov properties be problematic in real world applications? It's going to be because the real world applications don't always have, like, follow the Markov property. If you look at data, they often list like previous data and follows that trend. So that's why it could be hard to like look at that. That's basically it. Here's our standings.
Shit. Yeah, okay.
Congratulations.
Can you do the undergraduate sales class? Yeah, I took that when I first started. I think you recently.
No, oh, it's just
Who was the third person who was in the leader? Oh, okay. Awesome.